Welcome to this Armstrong Ceiling Solutions CPD video on specifying suspended ceilings for health and well-being. The learning objectives are to understand how building design impacts the health, well-being and productivity of occupants, understand the industry drivers and business case for higher quality, healthy and greener buildings, and evaluate the performance characteristics of ceiling systems which positively impact on well-being. This is today's agenda. These are some of the key facts and figures about Armstrong. These are the main topics we will cover and how they relate to user comforts. As the world's consumption of natural resources continues to grow at an increasing rate, the design and manufacture of environmentally responsible products for use in the built environment is no longer a nice-to-have, but a necessity. From mobile phones to clothing, food crops to building products, producers are giving increased attention to the materials, ingredients, and the environmental impact of their goods across the entire product life cycle. A new era has begun for the building and construction sector that is transforming the way products are designed, measured, and specified. Buildings are complex. They provide shelter, act as communication and data terminals, as well as centers of healing, education, justice, and community. They are expensive to build and difficult to maintain effectively over their life cycle. The economics of the built environment have become as complex as building design. Costs of ill health vary by sector and country and are rarely comparable, but the impact is clear. The annual absenteeism rate in the US is 3% per employee in the private sector and 4% in the public sector, costing employers $2,074 and $2,502 per employee per year respectively. Poor mental health specifically costs UK employers £30 billion a year through lost production, recruitment and absence. The aggregate cost to business of ill health and absenteeism in Australia is estimated at $7 billion per year, while the cost of presenteeism, not fully functioning at work because of medical conditions, is estimated to be $26 billion Australian dollars. This information comes from research from the British Council of Offices. It covers feedback received from office workers about their workplace conditions. This covers bugbears and main irritants and covers things they could put up with and problems that were unacceptable. Here are some of the common topics. Here we start to put some weight behind individual topics, from physical well-being, as we spend over 70% of our time at work. The working environment has a large impact on our mental state. Acoustics cover a large area of the workplace, from general conditions in the office to causes of problems in certain areas such as communal or dining areas, as well as privacy in small cellular offices or large open plan areas. The components of indoor environment include indoor air quality, thermal comfort, lighting and daylighting, and noise and acoustics, resulting in the following negative outcomes: indoor air quality, headaches and breathing disorders; thermal comfort, fatigue and discomfort; lighting and daylighting, eye strain and headaches; noise and acoustics, lower productivity and poor concentration. User-centered design challenges what we would consider as conventional design, where the project is divided up into small parts and involves individual team members. Each is looking at their own section and not always considering the whole project and how people will interact with it. The integrated approach is designed by a whole team at the same time, where all options can be considered and improved upon. Key seminal research in 2003 identified 15 studies linking improved ventilation with up to 11% gains in productivity, as a result of increased outside air rates, dedicated delivery of fresh air to the workstation, and reduced levels of pollutants. A meta-analysis of 2006 of 24 studies, including 6 office studies, found that poor air quality and elevated temperatures consistently lowered performance by up to 10% on measures such as typing speed and units output. This analysis appeared to demonstrate that the optimum ventilation rate is between 20 and 30 litres per second, with benefits tailing off from 30 up to 50 litres per second. This is significantly higher than minimum standards required, which are typically between 8 to 10 litres per second, although these vary considerably by country. Similarly, in a 2011 lab test which mimicked an office, a range of office-related tasks were carried out with the presence of airborne VOCs. Increasing ventilation from 5 litres per second to 20 litres per second improved performance by up to 8%. Reduced absences may also be a key indicator of the benefits of good indoor air quality for businesses. Short-term sick leave was found to be 35% lower in offices ventilated by an outdoor air supply rate of 24 litres per second compared to buildings with rates of 12 litres per second in a 2000 study. The same study estimated the value of increased ventilation to be $400 per employee per year. CO2 levels are one way to measure air quality and can occur as a result of poor ventilation. High CO2 levels have been found to impact tiredness or decision-making in a number of studies. One recent lab-based study using simulated decision-making tasks showed CO2 having a significant detrimental impact. 11% to 23% worse at 1,000 parts per million ppm compared to 600 ppm, despite 1,000 ppm being widely considered acceptable. Indoor air quality (IAQ), chemical indoor air pollutants, i.e. lead, formaldehyde, other VOCs. 30% of new and renovated buildings receive excessive complaints related to IAQ. World Health Organization. 91% of building owners list greater worker productivity as the return on investment benefit of healthy building investments. Indoor air quality can be measured by the products used in construction. M1 is the short version name of the Finnish voluntary emission classification of building materials. M1 is the name of the lowest emission class of that system. The emission classification of construction products for interior use is based on an emission chamber test after 28 days. Chemical testing parameters are TVOC, 1A and 1B carcinogens, EU classification, formaldehyde, ammonia, and an odor acceptability test, modified ISO 16000-28 test or CLIMPAG test. Odor shall be neutral or better acceptable under the test conditions. M1 emissions testing for materials help to achieve certain credits within BREEAM or LEED building rating systems. VOCs are also measured via the CE marking route. Good floor-to-ceiling heights not only feel like large spaces but also help to improve air quality. The stratification of air combined with good ventilation allows air to mix well and reduces the buildup of CO2. Selecting the appropriate materials help to construct a low VOC space, leaving a clean and healthy space in which to work. Clean room environments prevent dirt and other unwanted particles entering the room from void spaces and dirty rooms. A discrete particle counting light scattering instrument is used to determine the concentration of airborne particles, equal to and larger than the specified sizes at designated sampling locations. Small numbers refer to ISO 14644-1 standards, which specify the decimal logarithm of the number of particles 0.1 um or larger permitted per meter cubed of air. So, for example, an ISO Class 5 cleanroom has at most 10 to the power of 5 particles per meter cubed. ISO 14644-1 assume log-log relationships between particle size and particle concentration. For that reason, zero particle concentration does not exist. The table locations without entries are no applicable combinations of particle sizes and cleanliness classes, and should not be read as zero. This allows research in labs or manufacturing of high-tech materials to be carried out without contamination. The lower the ISO class, the better the performance. Kinetic of particle decontamination class. When air quality is reduced by a peak of pollution, the airflow system must return the level of particle cleanliness back to the initial ISO level within a certain time limit, depending upon the risk zone. A ceiling tile must not retain this pollution and be able to release it a long time after the initial pollution. It is tested for the kinetic of decontamination, which, for a particle of 0.5 UM, is defined as the time necessary to decontaminate the tile by 90% compared with the initial peak of pollution. The amount of time taken to reach this level of decontamination defines the class it achieves as per the below table. An analysis in 2006 of 24 studies on the relationship between temperature and performance indicated a 10% reduction in performance at both 30 degrees C and 15 degrees C compared with a baseline between 21 degrees C and 23 degrees C, leaving little doubt as to the impact thermal comfort has on office occupants. A 2007 study analysed the capital cost, energy cost and indoor air quality benefit through health and productivity improvements of 6 heating, ventilation and air conditioning HVAC strategies for the Australian climate and market. It concluded that displacement ventilation with circulation of 100% fresh air was the optimal choice for maximising indoor air quality and thermal comfort, while minimising energy costs. It was estimated this option added $248 per square metre per year in value for tenants. To create the same thermal capacity as 3 cm plasterboard containing 30% PCM, you will need 14 cm of concrete or 18 cm of bricks. PCM allows high thermal mass properties to be added to lightweight construction which could not support bricks or concrete. By using lightweight construction, it is possible to reduce building costs and running cost of the project. In this graph, the red line shows the temperature fluctuation throughout an office space over a week without an installation of PCM material. The blue line shows the same fluctuations over the week, but this time with PCM materials added to the office space. The use of PCM material adjusts the thermal comfort of the room. The very high temperatures of 32 degrees C are not reached with PCM, as the excess heat is stored within the product. This heat is then released at night when the room cools down, so the room does not reach the low temperature of 18 degrees C. This process and ability to store excess heat energy creates an improved temperature stability throughout the working day. The temperature drop in the evening has the effect of resetting the PCM for the next day or cycle. PCM is trapping heat from room during the day, and recrystallization as the temperature drops helps to recharge the PCM. As heat rises, the ceiling is the perfect place to install PCM and take advantage of its heat storage ability. These PCM cassettes use the micronal PCM and adds it to a suspended ceiling tile. The PCM insert is sandwiched by 2 metal ceiling tiles. This is done to ensure good fire reaction performance, but also allows a reversible tile to be used with an 8mm or 16mm drop. The metal tile also allows good heat transfer through itself and therefore does not act as an insulator such as some plasterboard solutions. The tiles are designed to drop into a standard suspended ceiling grid system, so installation is very quick and simple. Grid strengthening may be required as the PCM cassettes are approximately 9 kg per unit. As the PCM is contained within the ceiling tile, the product becomes portable and can therefore be moved to problem areas or even taken with the client if they leave and move to a new building. A standard metal ceiling tile warms up as the temperature of the room increases. This is seen by the green and red colors on the tile on the left. With the PCM insert, as the room temperature increases, the heat is pulled through the metal tile and into the PCM. The surface temperature of the PCM tile remains cool. This can be seen by the blue color on the tile on the right. This continues until the heat capacity of the unit is used up. The wax has changed completely from solid to liquid. After this time, the room will continue to heat up if the heating load on the room remains at the same level. The graph shows the difference between a standard ceiling and a PCM ceiling throughout one day. For the standard ceiling, the room heats up with the heating load of a typical working office: people, computers, printers, lighting, etc. At a certain point, the air conditioning is triggered. This then cools the room and shuts off. The room continues to heat and the air conditioning comes on again. This cycle continues until the heat load on the room is removed. The office closes for the night. With the PCM ceiling, the room does not overheat. Any excess heat above the set point of 24 degrees C is absorbed by the PCM, and the air conditioning is not triggered. An even, comfortable temperature is maintained, and the energy and therefore cost of that energy associated with the air conditioning is saved. In the cool evening, in the absence of the heating load, the PCM tiles gradually cool, return to solid form, and drop the heat energy they have stored back into the room. This means that the room is not too cool first thing in the morning, but at a comfortable working temperature, and the PCM tiles are reset for another working day. For a typical office space, the room gradually heats up as the thermal load increases through the day. Number of people, computers, printers, lights, etc. Once the room temperature reaches the PCM set point of 24 degrees C, the PCM is activated and the wax begins to melt. A typical loading of 50% of the ceiling having PCM tiles will, in an average office, maintain the temperature at 24 degrees C for up to 4 to 5 hours. After this point, all wax has melted and the temperature of the room will begin to increase. The other 50% of tiles can be service tiles or standard acoustic ceiling tiles. PCM tiles should not be cut and so are not suitable for perimeter cuts or service penetrations. The speed at which the wax melts and thus the delay before the room temperature increases depends on the heat load produced inside the room. At the end of the working day, when the heat load on the room is removed or reduced, the purging process can begin. This process resets the PCM tiles for the next day by cooling the tiles below 24 degrees C and changing the phase from a liquid back into a solid. This process releases the heat energy held within the tile back into the room. There are a number of different ways of creating this purge, whether natural ventilation from the cool outside air to making use of lower tariff energy costs and using air conditioning. Whichever method is used, the purge is a critical part of the system as it resets the tiles for the next working day and thus gives the maximum thermal capacity to combat the thermal load generated within the room. Where existing thermal mass has been activated and acoustical absorption is also required, canopies or baffles can be used to maintain the airflow for heat to be absorbed into the concrete soffits and then pushed back into the room at night while giving adequate sound absorption within the room. Whether to use canopies or baffles depends on the amount of sound absorption required and the open space required for airflow to the thermal mass. A study in 1998 found that there was up to a 66% drop in performance for a Memory for Pros task when participants were exposed to different types of background noise. A follow-up study by the same authors in 2005 found that 99% of people surveyed reported that their concentration was impaired by office noise such as unanswered phones and background speech. The acoustic properties we need to look at are intelligibility within, privacy between, issues affecting occupants, reflections and echoes, reverberation time. The following are the recommended acoustic ceiling solutions for the different areas within a project. Collaboration, within a team, office building collaboration areas. Interactions and learning activities require open communications within groups, likely to be open plan design. Speech intelligibility is key. Between teams, need for moderate acoustic separation between different groups and significant acoustic separation from focus areas and privacy areas. Noise is key on distraction. Focus, within a space. Office focus areas. Knowledge workers can concentrate on individual work needs. These will most likely be open plan areas. Noise and low distractions are key. Between spaces. Important to minimize transfer of sound in all directions. Design factors include architectural technology enhancements, behavioral directives. Privacy. Within a space. Office building privacy areas. Knowledge workers, management, legal, financial, HR, etc. can concentrate on individual work needs and have confidential discussions. Most likely closed plan areas. Noise and especially privacy are key. Between spaces. Important to minimize sound transfer in all directions. Design factors include primarily robust choices of architectural elements. A comprehensive study in 2008 conducted measurements of the physical environment and occupant satisfaction for 779 workstations in 9 different buildings and suggested that lack of access to a window was the biggest risk factor for dissatisfaction with lighting. A recent study by neuroscientists suggested that office workers with windows received 173% more white light exposure during work hours and slept an average of 46 minutes more per night. Workers without windows reported poorer scores than their counterparts on quality of life measures related to physical problems and vitality, as well as poorer outcomes on measures of overall sleep quality, sleep efficiency, sleep disturbances, and daytime dysfunction. A study in 2011 investigated the relationship between view quality, daylighting, and sick leave of employees in administration offices of Northwest University campus. Taken together, the two variables explained 6.5% of the variation in sick leave, which was statistically significant. Light reflectance maximizes the use of natural daylight, but can also reduce the amount of lighting required in the hours of darkness. Large windows to the outside also improve visual comfort and the user's connection to the outside. Having large expanses of glazing can also increase solar gains into the building and increase the chances of glare. Suitable measures for solar shading and treatments to the glazing can counteract this issue. Light reflectance can contribute to a number of credits on building rating tools. Indirect lighting can light a space without the need for additional lighting when high light reflectance materials are used. Here's an example of indirect lighting. By utilizing the ceiling system and selecting a tile with high light reflectance, the depths of rooms can benefit from the same light levels as the areas close to the windows with only low indirect lighting. These divided spaces are common in offices where private booths are required to work efficiently with little acoustic distraction. These now do not need to be dim or gloomy artificial environments. Here are some of the benefits of indirect lighting and high light reflecting ceilings. These are the credits that can be achieved via the suspended ceiling for the user comforts we have covered. BREEAM, LEED and SCAR are the main rating tools used for offices, and the ceiling can contribute in a number of different sections. Old ceiling tiles can also be recycled if a refurbishment project is undertaken. This recycling process can also achieve further credits in all 3 rating tools. The maximised return on investment for all strategies designed to benefit occupants are: lower employment cost per employee, higher staff retention, reduced absence, optimised green building ratings, greater staff productivity, reduced health issues. Key spaces such as the ground floor reception utilised linear metal plank solutions with integral light fittings with acoustic infill to create a dynamic, light and airy feel to the main visitor experience. Suspended acoustic rectangular and square canopies on the black plasterboard background provided optimum acoustics as well as variety and interest to the main refectory. Classrooms benefited from the additional reflected light from white metal ceilings throughout for background lighting. Metal tiles incorporating phase change material (PCM), which absorbs heat during the day and releases it at night to reduce a building's reliance on air conditioning. Mineral C2C certified tiles feature a bright white surface with 87% light reflectance to help achieve 16% cost savings compared with indirect lighting. Manufactured with up to 64% recycled content and 100% recyclable, they offer both sound absorption and attenuation for optimum acoustic performance. That concludes this CPD video on specifying suspended ceilings for health and well-being. You can now take the CPD quiz.